Right. So welcome everyone to Mur Ligase November meeting. And I will just get the right page, which I can't now find, thankfully. 1 second. 1 second. And then I'll make sure that everyone's got the right screen up here. Okay. Okay, so welcome everybody, and a bunch of things for us to talk about today. I'm not sure where to start, actually. I guess if anyone wants to go first, that's great. Otherwise, we can take it in order of the actions here. If anyone has anything, big and overarching they want to say initially, that would be fine.
So Matt, do you want to have people kind of introduce themselves a little bit to Jan?
Yeah, sorry, I forgot about that. Yeah, that would be great. I mean, Jan, do you want to go first? And then maybe each of us can say what about who we are?
Sure. That sounds good. Hello, everybody. My name is Jan Abendroth. I've been crystallographer here on Bainbridge Island, just at the outskirts of Seattle, for about 15 years, close to 15 years. I've been working for SSGCID since its inception. We are in our 15th year now, have deposited close to 400 structures for SSGCID. And Peter had asked me to take over, Peter Horani, my colleague here, had asked me to take over the leadership on this project, push some structures over the finish line. So that's
Great.
what I'm hoping to do.
Thanks. I think we're going to be talking about one of those.
Mm-hmm.
Today. All right, I'll dictate the screen order. So I'm Matt Todd. I'm at University College London, and we have a lab there with a few people who are looking at the Mur Ligases as a project. And background is in organic chemistry and medicinal chemistry and open science. Bart, I guess you know. Right, and Chris Swain, do you want to go next?
Okay, my name is Chris Swain. I'm a drug discovery consultant. I worked for Merck for 20 years. In the last 16 years, I've been doing consultancy with a range of companies.
And then next is Laura. If she's there.
Yeah, yes, hi. So I'm Laura. Let me put my video on so you can see me. Hi. I'm working with Chris Dawson as a postdoc, and I'm mainly doing crystallography and running the XChem for this Mur Ligase project.
Great, thanks. And Dana's next.
Hi, I'm Dana. I'm a postdoc in Matt's lab in London, and I'm doing mainly synthesis and compound design.
Great. And then next is Laurie.
Hi, my name is Laurie. I am a research faculty member at Northeastern University in Boston, and I'm a medicinal chemist by training. And yeah, lovely to meet you.
And then Joe.
Hi, Jan. So I'm a computational chemist. I'm ex-AstraZeneca. I was at AstraZeneca for 15 years, worked on the Mur Ligases. I'm currently, I have a couple different roles, but I'm currently a visiting scientist at Northeastern in Laurie's lab. And we're working, on a number of different projects together.
Great. One of the two people in the team with the longest experience of working with Mur Ligases. And then Kato. You're muted if you're trying to talk still. Technical issue. That's
yeah,
it.
I don't know which mic is
Too many bits
used now,
hardware.
but yeah, I'm Kato. I'm an Erasmus student from Belgium, KU Leuven, and I'm a drug developer by training and now working in Matt's lab under the supervision of Dana. I work on fragment-based drug design.
All right, thank you. And then Chris Dowson.
Oh, hi. Chris Dowson, Warwick University, 25 years, a lot of that doing Mur Ligase things for the last 15 or 16 years, I think, and really helping to support biochemistry input and some of the structural biology input, so assay development, I suppose, and then structure-enabled discovery after that.
Fantastic, thanks. And then Yuhang.
Hi, everyone. I'm I'm the first year PhD student in math group. So I'm do some synthesis and a little bit computational. Right.
And then Zige, did you want to say a few words?
I'm a master's student with math, but I actually don't know what I'm doing right now. Still looking for the
We're going to solve
topic.
that.
Yeah.
Okay, thanks. And Frank,
Don't worry about that. You're like the rest of us. Most of us don't know what we're doing either.
Yeah, I was about to say, you're in great company. I've got no bloody idea. Frank Abendroth, crystallographer at Diamond. I run the XChem facility and sort of part-time interested in AMR questions. We're trying to help as possible.
Awesome, thank you. Lizbe?
Okay, so I'm Lizbe and I'm a postdoc in Frank's lab.
All right, simple. And Shah, do you want to just say quickly what you do? Please with us.
Hi, my name is Shah Choudhury. I just started the drug discovery course this summer this year.
Great. All right, and then Jan, oh, you joined us.
Yes. So yeah, Jan Jensen, a computational chemist at University of Copenhagen. So we're currently working on trying to help with docking studies. I don't know how much we're helping, but we're docking.
All right, great, thanks. And Laurie is there again, but I think you've had your turn, Laurie. You can't have it again. So I think you must have left and then come back in, like gone to the back of the queue again. All right, so I think it's everybody. Great.
Thank you all for the introductions. That was very nice. Nice working with you all.
Okie doke. Okay, so I guess I'm happy just to go through some things and try and speed through things through everything in the hour. I mean, Laura, one of the first thing here is, I guess, something that you posted quite recently about. You were taking some of the atom-wise compounds, I think it was, and working on SPR binding assays. Is that right, with Mur?
Yeah, I wanted to optimize the assay and then run the atom-wise compounds library against the Mur, CD, and E. But they are not happy on the CN5 sensor. So I bought a new sensor. They sent me a message that it was shipped yesterday. So after this meeting, I'm gonna go to the area where we have all the orders, and I'm gonna see if it is there. In that case, then I will be doing the essays, trying to do the essays with the new sensor next week.
Okay, awesome. Is this, forgive my ignorance, is this the first time we've had an SPR assay for the Mur Ligases?
In this project, to my knowledge, it is, yeah.
But not generally speaking, has it been done before?
I couldn't find information on it. So if I have missed something, it could be possible, but I haven't seen any.
Right. Obviously, that's going to be really great orthogonal method, right?
Yeah, I think it's going to be interesting. We can do, more testing, competition, essays, those kind of things. So yeah, it could be interesting to have it.
Yeah. Okay. And Becca, I think, has been delayed in another meeting, but is working on, activity assays, and is due to do the dose in the next bit of the to-do list. That is due to do the dose response experiments for the fragments, and I guess also for the atomized compounds. I mean, I'm assuming for Mur D and E, isn't it?
Yeah. So I think she's done the dose response for Mur D, and I was hoping that she'd be here to present it.
I think she's delayed in another meeting, she said.
She's emailed me and said she's having some plate reader issues, and she's got preliminary data, but nothing final yet, she said. So maybe she'll come later and say more about that, but that's the latest I've heard from her.
Okay.
I was also talking to Adrian about essays, because they are trying to optimize for a high throughput essay. And he gave me some preliminary results slides that I can show you later.
Oh, well, it's good to go now if you want to. No problem.
I can show you, yeah. He is not going to be able to join because he's working with trying to fix the problems that he haven't, but all right, give me a second. Okay.
We have an intermittent fault with the plate reader. It's a bit like one of those electrical faults with the car. You go to the garage and it's fine, then it's not. So
intermittent faults are the worst.
So I can show you these, what they have been doing. I'm not going to go into too much detail on how the assays work. You can ask him on the site. But this would be the assay for MURD, is different coupled enzymes, and they are measuring absorbance and fluorescence as well. And then this would be the one for MUR-E, again, the same system with the same coupled enzymes and the same absorbance readout and fluorescence readout. And they have been testing both spectrophotometric and fluorometric assays, but the fluorometric one seems to be the ones working better. So these were the results for 20 microliters, and it looks like there is a window for the assay, and yeah, looking quite good. So that would be the MUR-D results, and this would be the MUR-E results.
That's great. So it's 50 microliters. So that's
20 microliters. I think this is wrong. So he gave me two slides, one for 50 and another one for 20, but these are the results for 20. So I think this is just a typo.
Right.
But yeah, so this is 20 microliters and is looking quite good.
So that has implications for our ability to do the screen at European Leaf Factory, no?
Exactly. Yeah. It was been really good for doing the high throughput screens and be able to screen more.
Oh, that's great.
Yeah.
I think the aim is once the plate reader is serviced, or we switch plate readers, he's pretty confident that'll go down to 10 microliters, and that I think then that's the ELF format. Once we've got that with the parameters and a Z prime for them, which I'm keen for that to be very soon, before the end of the month.
Okay.
Communicate that with them.
Yeah.
Fantastic.
For those of you who were part of that
really,
conversation,
really good.
The European Leaf Factory were interested in this very much, and just wanted some more information on the ability to run a high throughput assay, and so this work is crucial for that.
Oh yeah, yeah, yes, yeah.
Sorry, Chris, you were going to
I've just said that this is fantastic news. I think having access to the European Leaf Factory will be a really interesting exercise.
Yeah, definitely.
Awesome. All right. Yeah, sorry, is there anything else you wanted to add to that?
No, that's all of it. Like, if you want to follow up with him, you can do later. But yeah, he just wanted to mention this is ongoing.
Right. Okay, wonderful.
And looking promising.
Yeah. Okay, any other questions? If not, if I could rest back screen control.
Yeah. I can't stop it now.
Okay, there you go. All right, excellent. So there was one question which came up. Yuhang and I were talking earlier today, and I guess we were wondering about the known AZ active that he shipped to both SSGCID and also you guys. I mean, is there advantage in measuring the activity of that supposedly known active versus D&E, or is that, I mean, just to make sure it's fine that we have a positive control and that it's active against both? Joe, is there a point in that? Because we know it's an active, and is there a point in doing that just for one compound for two enzymes, or?
I guess the question becomes actually which species do you actually have? Because I don't know. I'm a little confused about it. I think, as far as I know, there's no Pseudomonas assays for your C or D or E in Warwick. So
sorry, Joe. That there are assays for all of those.
But yeah, but okay, yeah, okay.
And I did say that they were getting out, and I did say he was going to do them, that Julie was going to have a go at running those assays.
But okay, so that would be interesting to have them. I just haven't heard that. Or seen any results in the last
no,
couple of
because
years.
we still haven't signed off the paperwork with AstraZeneca to get the compounds to Warwick.
Yeah, but I'm just okay. I don't want to. I'm not going to get into old history here about compounds that haven't been assayed for forever. So anyway, but yeah, if there's, I mean, I think if there's an assay for Pseudomonas or E. coli Mur D, it would be good to get the AZ compounds assayed. Yes. Because
the paper that your paper is just Mur C, right?
That's correct.
Okay, so I mean, it would be interesting data if it's potent against another, right? Okay, and I guess I wanted to ask people's opinion on the atomized compounds. I mean, if this is a reasonably high throughput assay and it's running, then is it worth just having a go at those compounds, the ones that were found to be
Sorry, Matt, I just had one last question to Joe. Would you expect those compounds to have some activity against D and E?
Yeah,
probably for D, I would hope so. I mean, they're quite potent. They're low nanomolar compounds against C. Okay. So there's enough similar. I mean, this is the whole hypothesis that C and D are similar enough that you would hope that there would be some activity. So yes.
Thank you.
In terms of E and F, I'm not so sure. But that would obviously be interesting to get, a Mur E data point as well.
Yeah, I was just going to say the same thing. I think what you need to start building up a data set of activity across all of the enzymes.
Yeah. Okay. So yeah, Yuhang's compound should be active against more than one. I mean, that would be very nice. He's also making the other main AZ compound and a backup compound too. So there'll be more coming. He can briefly mention this in a minute, but yeah, I mean, as we generate these, we don't want to sort of send small numbers of compounds if that's a drag, but if compounds are being run anyway and we can slot those in, then that would be great. So with the atomized compounds, I mean, we have binders, right? We don't know how good they are. Is it worth just trying them in a biochemical assay to see what happens?
I'd say yes.
I don't want to commit people, right? I mean, it depends on resources.
I mean, yeah. I mean, yeah. So, I mean, honestly, the AstraZeneca stuff we would have done. We had those Pseudomonas Mur Ligase assays done 15 years ago. That's when we got when we had the reagents from Roger Levesque. So they exist. What we don't have is the paperwork to allow us to work on the compounds yet. I'm still pushing that through. So as soon as we have that, then we can work on it.
Right.
Okay. Yeah, but you have Yuhang's compound. So I mean, that's an AZ compound, so that's ready to go. So it's a question of timing. Do you want to wait for the the 3 AZ compounds, or do you want to move forward with the compound you have in hand from Yuhang's lab?
Yeah, I guess I was wondering about the combination of the atomized 8 that were found to have bound plus this one, and I mean it's a decent data.
Yeah,
set.
I think on the atom-wise compounds, based on Laura's data, it's the crystallography, right? I mean, they don't seem to be competitive, right? So I think the SPR assay is going to be just finding out, binding, and maybe I don't know what kind of competition Laura can do in the SPR assay itself, but I think on the biochemical side, I think it's going to might be a big challenge, would be my guess. I'm not an enzymologist, but I'm just thinking based on kind of the binding mode of those compounds. Mm-hmm. I'm not sure how that's going to match up with kind of the biochemical enzymology system that Chris has in his lab. But Chris maybe can speak more to that about these kind of potentially allosteric non-binding compounds and how that might manifest itself in his biochemical assays.
Yeah,
we'll have to see as to, yeah, we'll have to see.
Okay. All right.
I'm not sure which compounds are being discussed here, but we received 3 compounds and tested them against Mur C and Mur D from Pseudomonas and Acinetobacter. And they all were positive with good shifts in thermal flow assays for Mur C, but they didn't show any shifts at all for Mur D.
Yeah, we're talking about biochemical assay.
Yeah.
Right.
But even the binding assays didn't show anything for Mur D.
Well, I'm a little confused here, Jan. So you're doing a biochemical assays at SSGCID? I thought these were like this.
We're doing binding assays.
Right, not biochemical. These, yeah. This was the that micro assay that
Yeah.
Peter's talked about in the past.
I would think so. Yeah. Yeah.
These three.
Actually, I don't know. It's AZ22, AZ13, and AZ26.
Yeah, those are the compounds that you received.
Yeah.
And so you did the you incubated those with Mur D and got no indication of a binding interaction.
Yeah, I can just quickly share my screen here.
That would be a bit of a surprise, no?
So this is SSGCID nomenclature for Mur C, Pseudomonas, Acinetobacter. This is
Can you go
Mur
to full
D.
screen? Can you go to full screen, please?
Yep. Yep.
Thank you.
Oh, that just totally disappeared for me.
It's thinking.
I just got a black screen. I've never had that.
If you just, yeah, I would come out of that. We can see a partial screen, at least I can. If you come out of that and then just maybe minimize the thumbnails on the left, it'll get bigger.
So is that okay?
I can only see a fragment of the slide.
Right.
Don't know about anybody else.
Yeah, sorry about that. Maybe just go back to present, not full screen mode, I guess.
Yeah.
Sorry.
It is in just standard edit mode. Let me just unshare my screen.
Okay.
Maybe stop sharing and reshare.
Yeah. That's a new one. So,
okay.
Is that any better?
Yeah, I can see.
Okay. So the first two lines here, this is Pseudomonas, this is Acinetobacter, 137 is Mur C, and 17938 is Mur D. And these are the three compounds that were tested in the DSF assay. We got very nice strong shifts for the two Mur Cs, and we got virtually no shifts at all for the Mur Ds. Again, these were binding assays, no biochemical assays, but you would assume that biochemical assays would require a positive binding assay. Unless there are some conditions that we didn't consider that we need to pre-incubate with a cofactor or something.
So I guess one of the issues, sorry. So
Yeah.
I mean, it is, thanks for, I mean, this is great. I mean, getting this kind of data. I mean, I guess one of the things here, you're kind of crossing Acinetobacter and Pseudomonas. And so then, I mean, there are some differences there.
Yeah.
You know, it'd be nice. I mean, sorry to be asking for things, but obviously it'd be nice to have Pseudomonas Mur D as opposed to Acinetobacter Mur D, but it is what it is.
No, we tested all of them. We tested Acinetobacter and Pseudomonas.
Oh, so the bottom one is Pseudomonas Mur D. My bad.
Yeah, the bottom two, everything that is 179.
My bad.
Yeah.
Sorry.
Okay. No, they were all tested.
Wow. Important data.
Yeah, and I think data is fairly convincing to me.
And that's all three.
Yeah.
So actually in this, I'm curious here. So is this in the presence? This is, okay. So one of the discussions that's been going on a little bit is the dynamics of, for example, Mur D. So if you look at the literature, there's an open form. And then basically when you have like ATP bound, then you get more of a closed form. So I guess the question here would be a little bit about, you know, the dynamics and these, you know, whether these are inducing, you know, the closed form of Mur D or not. So anyway, that's one of the things around Mur D. I know there's been some discussion on GitHub about this. And also there's papers been published about the dynamics of Mur D. But you would have hoped that, you know, the potency of these compounds against Mur D would be enough to maybe induce, you know, this binding and closing of Mur D, but evidently not.
Yeah.
did we have data of this kind with Yuhang's compound? The other, it's another AZ. It's not the same, is it? Am I confusing myself?
No, it's it'd be a fourth compound. It'd be a fourth compound, Matt.
Yeah.
Yeah.
So I think they were made. I don't recollect what the results were. I have a feeling it was very similar.
That Murdy also was giving no shift.
Yeah.
If you were able to merge this with that compound, then we'd have a full set here. That would be really interesting.
Yeah.
If that's all right. And
yeah.
To be sure, because that's a, I mean, there's a very promising core with lots of variation in the what is it, southwest, where we'd expect something to hit. So we need to figure out why.
Yeah, I can rally up that information and forward it to the team.
Great. All right, thanks. Wow, surprising.
I'm just wondering, I mean, just trying to pull a rabbit out of the hat here. If this was done with in the presence of ATP, and then the question would be, would these compound? I mean, I'm just thinking about, you know, just the dynamics of this, and I'm wondering if it was done in the presence of ADP, for example, and you know, would you be able to see any competition, any kind of shifts, and is that at all make sense or not to try?
I'm out of my depth. Chris, yeah.
Yeah. It's worthwhile trying, but I would sort of refer to the experts here on the team on MUR-D to give advice if that's what you would expect, or if that's grasping for straws.
Well, we know dynamics, but yeah, maybe Chris Dawson. I mean,
yeah, I was going to say,
where are we, Chris?
it may be we're already loaded up with ADP anyway in the process of protein purification. So unless you know that there isn't any in there, just because you haven't added it doesn't mean it's not there already. So it may already be there.
I actually don't think, because I have solved structures for both the Acinetobacter and the Pseudomonas, and there was no ADP bound.
Okay, good. Okay.
That, of course, you can argue that crystallization is a purification process, and it might favor the species that have ADP not bound.
Yeah.
So it's not 100% proof, but I think it's pretty convincing.
Yeah.
Actually, I don't remember. So I know there's an E. coli MUR-D structure. Did you say you solved a Pseudomonas MUR-D structure?
Yes, that is in peer review. So we just
I'm sorry, in what? I'm sorry.
So whenever we solve a structure here, it goes through internal peer review. So after a bit of struggling, I solved, I can actually show you.
This is the one that was just posted?
No, that's Acinetobacter.
No, the one Jan's just about to talk about.
Yeah.
So this one here, it's a structure that I solved just very recently. Whenever a crystallographer finishes up a structure, he or she sends it off to a colleague for peer review, where the colleague goes through the model atom by atom and double checks it, that is all good. And then it gets deposited to the PDB or forwarded to our collaborator.
Okay.
And that's where we are right now.
Oh.
So the structure is solved. You can see the ribbon diagram here. It's got 2 copies in the asymmetric unit, which do a little bit of this sort of wobbling, opening and closing between the 2 of them. And my hope is that within like 2 or 3 weeks, it's ready for delivery to you guys and the PDB.
That's awesome.
Yeah. And then the next one was the one that you've already deposited.
The next one here, that is the Acinetobacter, and that has been deposited in the PDB with 7SIR as the PDB code, no X.
So you don't think it's going to be possible to soak the AZ compounds into the MUR-D given your thermal shift assay? Is that your conclusion? Or are you going to have a go at that?
We don't have many crystals, so it's not that I have a lot of crystals where we can soak them in. I think chances are very low. Chances are a lot higher with Mur C, and these actually the crystallization with all three compounds and the Mur C, of which we have a lot of, is already going on. The other, so sorry, I'm taking over the presentation here. So
nice
for the Acinetobacter Mur C, we have lots of protein. So I already went ahead and set up crystallization trays with that. While for the Pseudomonas Mur C, we have rather little. So I wanted to wait for your advice what to do with it. And we can do anything, but when the protein is used up, it'll take a while until we have resupply. So I want to use it wisely.
So I would think, I don't know, I mean, getting a structure of Acinetobacter, one of the compounds in Mur C, I mean, again, kind of Chris Swain was talking about, I mean, this kind of building out a portfolio here.
Mm-hmm.
Even though it's, I mean, we're trying to get dual inhibitors against 2 Mur Ligases, at least getting a second species against Mur C structure, I think would be valuable.
Yeah.
Presumably with the Mur D structure, we need to try to model why the compound might not be binding. I mean, it's the, you know,
absolutely.
Mm-hmm.
Absolutely.
Hopefully people on this call want to have a pop at that because it seems quite important to me.
Well, once we get the structure from Jan and the team at SSGCID, we can do that. But I don't want to, you know, they have a process, and we have to respect their process.
Yeah.
So,
but one of these was just posted that you want to.
No, that was Acinetobacter.
Yeah, is that no good? We don't want to do that. I mean, obviously, you want to compare the same species, right?
Yeah. So this one here is available, and you see an overlay of the. In purple, you see the Pseudomonas structure by comparison. So not surprisingly, it's quite similar. But as you said, we need to follow the process here, and then we can share the structure.
Okay, great. Any more comments, queries?
Okay. Caused enough disruption here to the process.
No, this is great stuff.
Well,
thank you. Thank you for all the efforts.
Yeah.
Okay. Okay, just let me go back. All right, so we've talked about most of this. I don't think I said already, it's on me to contact Atomwise to run through the results that we got from the soaking and check what they calculated. So I haven't had that conversation yet, sorry, but I will. Yuhang was just as an update. Yuhang, is it okay if I do this, because we're running a little short of time? You've prepared a very nice summary here of some synthesis that you've been doing. So to try and access the other AZ compound, Yuhang had a really nice solution to getting this really difficult intermediate, which he's solved. And now he's got a beautiful 1 gram of this intermediate over here. And so we can attach a bunch of different things onto this position, and we're going to go for the AZ compound first. And then there's a little snafu with a solvent attaching in its place, which we're currently dealing with. And then the idea is after that, after we've got that problem solved, to then, I mean, use this compound obviously, but also to convert the OH to the amine. And he's got a nice double step approach here, which is, you know, you got to pray a little bit to the gods of chemoselectivity that'll work, but it's not a bad punt. There are ways around this if it doesn't work, of making the diamine initially. And this is the backup compound also from AZ paper. And this could also be converted to the amine using this approach. So things are in progress, and Yuhang's been doing some tricky chemistry, but we're pretty confident that we're going to have the other AZ compound pretty soon. Okay, and for those of you not familiar with it, we're making this amine so that we can try and make the compound active against wild type organism.
For the compound 13, amine derivative, no, just this side. Yeah. For this side, we would just know that we just got the information from Yan, right? Like that, its alcohol form did not got good shift on the binding assay, so we're already expecting to get a good data from this structure, the amine derivative.
Okay.
Oh, that's in Mur. That's in Mur D, not Mur C.
Yeah.
So there's actually I don't know if in this slide there's the 3 AZ compounds that were sent to the SSGCID, but at least one of them was a basic compound, I think, or 2 of them. I can't remember now. Yeah. So you can see actually both compound 22 and 26 having a basic group in them.
Yeah.
Primary amine. So it'll be interesting, just even getting those structures to see kind of if they have any interactions at all within the protein.
Yeah.
But neither one of those had good gram-negative activity or wild-type gram-negative.
And sorry, just remind me, they were active in vitro, right?
They were active what?
I mean, against the enzyme and biochemical.
Yeah. They're active at the enzyme level, but none of the compounds that AZ was published out of the paper we did was active against wild-type gram-negative.
Right.
But they were all quite pretty low nanomolar inhibitors.
The obvious possibility here is that this carbamate group is cleaved and the amine makes no difference at all.
Right.
So I guess
it'll be interesting to see what's in the structure, right?
Yeah. Well, yeah. No, I mean, if you give it to the bacterium.
Correct. Yeah, that's true. That's true.
So in the case of Yuhang's compound, it's just got the amine there, so there's no way you can have that problem.
Yeah.
Okay. Great. All right, thanks. And then I guess the next thing that has been generating a bit of discussion was the predictions from Yan and the poses that were generated and which were posted earlier. So I guess Yuhang's been having a look at this, and Yan still with this, I think. Sorry, I've lost. Yes. Yeah. So I guess the structures that were deemed to be the most promising, which were commercially available, were the ones here. We've spotted that 2 are very similar, maybe aren't needed. The poses that came out are really interesting in the sense that I think this is the stuff that you did, right, Yuhang? So the yellow is the original AZ compound, and the greens here are the predicted compounds. So adjacent and a little bit overlapping, but a bit distinct. I don't know what to take away from that. The predictions are pretty solid, but do people want to just discuss these suggestions and whether we are ready to buy or whether there's more analysis that's needed?
Well, let me just say that we define a binding pocket, so it's not like an actual crystallization screen. So they can only bind what we tell them. So that says nothing really. So it's really about whether they make the contacts we think they should. And I don't have really, neither Casper and I have really the expertise. So we just threw it out there. And in terms of the protonation states, which were discussed, so we now use LigPrep, which basically tries all possible protonation states and tautomers, and we basically just pick the one with the best docking score. And so if that's not realistic, then maybe we should disregard it. Although I have to say that there are many examples of sort of a protonation state that's not likely in solution, right? That's sort of picked up. You can pick up a proton or you can lose a proton when you bind the active site. You take a hit in the docking score, which is not included. But I mean, there are plenty of examples where sort of an unusual protonation state is found in the actual dock.
Yeah, is the idea that the various protonation states which are being assessed are realistic. And so if they occur,
No.
I mean,
not realistic, but just we're showing you the best possible protonation state if you just consider the binding.
Yeah, no, that's what I mean. I mean, but you know, they're all available through equilibrium, right? Nothing's outlandish.
Yes, but,
right?
but
So,
you pay,
no, they're not. I mean, so a pyridine, pKa, I mean, Chris Swain can step in here probably as a better physical organic chemist, but the pKa of pyridine is what, 4.5, 5 or something like that. So
Yeah.
at neutral pH or in water, you know, again, this is assuming we're, you know, at physiological pH of 7.4, pyridine is not protonated. And so if you're going to bind a protonated pyridine, you're really pulling something out that is whatever, 199.001% present. Is that correct, Chris?
Yeah, that's true, unless you've got something like a 4-amino group on the pyridine, which will obviously make it more basic. Yeah.
Yeah, but it's pretty hard to get the pKa of a pyridine up to, I mean, one pH unit is a factor of 10, right? So pH, if you have a pKa of 6, that means you basically, you're tenfold, you're 1/10 of the population of in terms of what's present. Now you can talk about Le Chatillier's and do you actually the binding event pulls it out of solution, and et cetera, et cetera, et cetera. Yeah. So it's just it's fine. You will find cases. I would just say it's your risk. You're risky. You know, you're playing a lot of roulette here if you're hoping to bind a protonated pyridine. And just also on some of the, you know, on the scoring. I mean, I just lived with this forever. Scoring, the electrostatics in terms of the contribution of scoring functions tend to dominate. And so when you have salt bridges, they will make your scores look a hell of a lot better. And if you're not doing, you know, even the solvation terms that are out there, these kind of, what do you call it? They're not true, you know, you're not running free energy perturbation kind of calculations. The solvation terms are kind of not so great. So anyways, it's fine. I mean, I'm just trying to point out that those are some of the risk factors with these compounds, that your scores are being dominated somewhat by electrostatics, and you're also, the salt bridges you're forming are not necessarily with highly likely protonation states. So that's just my input. I try to want to just provide, you know, my feedback.
Yeah, and I don't disagree. I mean, you're absolutely correct in that. So if you're trying to narrow it down, I mean, I imagine these compounds are fairly expensive. If you're trying to narrow it down, throwing out an unlikely protonation state is a very good metric, sort of for excluding something. If you have other compounds with a more sort of realistic protonation state, yeah, I absolutely agree with that.
What's the you were mentioning? Joe, the salt bridge with one of the residues. What's the motif in these molecules that's doing that? Because they're all quite different here. What's the interaction?
Oh, it's just whether it's okay. It's either the protonated piperazine,
right,
or protonated pyridine. So if you look at in the top row, for example, the top row, the fourth compound from the right, that compound, that pyridine, is protonated, and you have basically the NH of the pyridine interacting with an aspartic acid side chain. Okay, and so that, you know, that part of that contribution to that glide score is coming from the electrostatic interaction between the positive charge on the pyridine and the negative charge of the aspartic acid side chain, and that's just, that makes your score look like, you know, it's a better scoring compound, but the likelihood that pyridine is protonated is low. So that's just what I'm saying. That makes that a risk. And so I would be looking, you know, you've done a lot of work here. You've done all the docking. When you go looking through the results, I would just think about, you know, which are the ones that are compounds that are, you know, forming salt bridges. And then if they are, what's the protonation state? And some of these are okay. Some of the piperazines like compound on the top left, is doubly protonated. It's never doubly protonated at physiological pH. It's the terminal nitrogen that will be protonated. That's the one that has the more basic pKa. And and that's fine. That that will be protonated at physiological pH, and so that in terms of its score is the interaction is fine. It's a question of that score of -8 is still again being dominated by an electrostatic interaction.
Okay.
Sorry, I'm just going on and on, but
no, this is
I'll stop here. I'll stop here.
No, because we need to have a plan for what we're doing with these molecules, right? And we want to buy some stuff that's predicted to be good, because it's important to get experimental data to so we know how these predictions are doing. But we just want to be sure. That's all, as best we can. So the points you're making are very good.
I think the other point I would add is if you have salt bridges and things like this, if it's a buried salt bridge, then you can probably believe it. If it's one that's on the surface of the protein, I think you'll find that you'll struggle to compete with water.
Excellent point, Chris. Thanks for that.
Great.
Okay. Let me just point out that compound 2 we're talking about. So that's the number 4, basically, from the top. Is that, or was it 4 from the top? That one?
The protonated pyridine of this guy, yeah.
Yeah, that also has a very high log P. So it may not be soluble.
Unless the pyridine's protonated.
Unless the pyridine.
Stop it.
Well, it definitely won't be protonated in solution. We're arguing about whether it's protonated in the but even if it's unprotonated, this will have a high log P. So I'd be worried about the solubility of that particular one.
Examining the protonation states, how easy is that for someone like me who doesn't do a lot of modeling? You have to look at the poses, as was done, right?
Well, I mean, the critical thing here, Matt, I mean, I think, as I recall, maybe a physical, organic, synthetic chemist. And so I think your pKa's pretty well. You can look at molecules and know what's going to be protonated and not be protonated. And so that's the first step, really, is, this is always, again, Jan, I'm not, please don't take this the wrong way, but it's just, when you use these automated programs, especially, and I've just dealt with this many times in the Schrodinger software, their pKa predictions, what things get protonated, is not always the best. And you just got to use your science, of understanding what pKa's are of different groups and what should and shouldn't be protonated. Like I said, you see in these things where, like, piperazines get diprotonated. Well, the chance of a piperazine being diprotonated is like nil, and the pKa of a pyridine. So again, I'm gonna stop here. I gotta stop. We got time taking up too much of this meeting.
I guess what I meant was the green structures we're looking at here. It would be nice to see what the protonation state is that is leading to the binding, and therefore how we can triage these suggestions easily, right? So we can triage by log P, and we can triage by cost, but how do we triage by, for example, realistic protonation state?
I think you have to look at them one by one.
That's what I mean.
Bound into the active site.
That's what I mean. So I guess you just have to look at them and then check the protonation state and then triage it.
I uploaded the Maestro file this morning, and that's when I kind of started to look at them. And so I can post a Maestro file, or there is a Maestro file, I think, that Jan already posted to the GitHub. That's why I pulled it down from. Okay. And so you can just pull that into Maestro and Schrodinger, and you can look at the structures, and you can see which ones are protonated, and make a judgment.
Great. Okay. I'll go and look over Yuhang's shoulder in the lab, and we can look at that.
Yeah. So just a comment. So this is the best possible score, the protonation state. So if you don't like the protonation state, the score is going to be worse. Yeah. So you can sort of triage that way.
That's what I mean. Yeah. And so if we do that and we get rid of 8 of these, there are others in the wings waiting to come along that we could then look at, right?
Well, actually, no. So not from the purchasable compounds. So these are all the compounds with a score lower than 7, which is basically what we think is reasonable for binding. So that's basically all the ones we found. So yeah, from that are purchasable from this library.
Okay. Okay. And
anything else will have a lower score that we deem sort of likely to be non-binders.
Interesting.
Yeah.
I think I guess I would push back on that a little bit, Yuhang, just in the sense that, I think if I recall, you're using that -7 score as kind of what the AZ compound scored. An AZ compound.
No, actually, no. We use it's actually based on the analysis of this. So it's with the Scheuchert article where he had like it's a completely different protein. So that's the caveat. But we basically there is this, if you go further up in the issue, there's a set of about 500 compounds that Brian Scheuchert measured for a kinase. And we basically just computed, not in this issue, the original issue.
Right.
Yeah. So we basically computed sort of the likelihood of being a good binder based on the glide score. And basically if it's less than -7, it has about a 50-50 chance. If it's higher than 7, it has like a 25% chance. But I mean, that's of course assuming that the Scheuchert kinase is representative of this protein, but that's basically the best we got.
Yeah, I mean, these are, I guess I look at these as most of these are, I would put them in most of these in the fragment class. They're relatively small. Most of these are molecular weights, I assume, are probably under 300 or not much above. Right. And so, these being, a 10 micromolar or even 50 micromolar inhibitor, I mean, that's still, these are all novel, right? So I don't know. I wouldn't necessarily, I understand where you're coming from, and it's all logical in terms of using that Scheuchert kinase thing, but I'm not sure I would just, I might be a little bit more aggressive here in terms of thinking about some of the other compounds that might be a little bit lower. Okay. What's the difference between -6 and -7, I guess is my question when you look at the poses. So something you might think about.
Okay,
I'd agree there, especially if you have the SBR assay available.
Yeah, we can throw up more with worse score. It's just the only data we really have to go on is the Scheuchert, and it just drops from 50% to 25% when you go below 7. That's basically all we have to go by.
Just ideally.
Maybe I'll follow up with Yuhang offline. I got some other things, but I got to stop.
Yeah.
I just the background thing here is that it would be great to get to a point where we're happy to buy commerce to validate the predictions here. That's all, but we need to be sure before we do that. All right. So yeah, that's the most key issues have been talked about here. I think there's a bunch of other older actions here. A bunch of other smaller things here. Anyone want to talk about something in the last few minutes that is important to everybody that we haven't managed to get to yet? Anything at all?
Well, just to mention, I got the initial hits for the initial crystallization hits for E. coli MURD. So I'm following them up, and I'm gonna send the Fer crystals to Diamond next week and see if they're good enough for the next steps and so on. So yeah.
Sorry, which compounds are you talking about that have been soaked in?
No, this is for the APO for doing next chem. I might pop in the compound. The compound, I can't remember the name. Yuhang sent me a compound. Can't remember the name of it.
Yeah,
yeah, so I was gonna try to soak, but they don't look that promising, so they look very fragile. So I'm trying to get follow-ups, and if those work out, by the time I'm freezing crystals, then I will prepare soaking.
Yeah, don't worry, if you run them out, I can just make them directly and send them back again.
That's fine. I think we should be fine, but yeah, it just depends on how it goes with the crystal. But yeah, anyway, I'm working on it, and I hope we can have it soon. Set it up. Yeah.
And Laurie, just a quick question about the Cyclica input. I guess we have invited Cyclica to the meeting, didn't make it today, but maybe at a future one.
Yeah, I'm still having issues in terms of trying to get any kind of agreement through. I'm actually going to reach out to them today and see if I can organize a meeting and just see if there's a way we can push this through some other way.
Okay.
Sorry.
No, great. All right, good, thanks. Anything else anyone wants to mention?
So just about 1 minute, sorry, just about the Yang's suggestion and Joe's suggestion. Do we need to take the overprotonated structures and manually fix the pH protonating state, and then like redock so that we won't miss any potentially useful structures?
I think
so. No, we don't need that, because the score is going to go down. So if you're not happy with this score, if you choose any other protonation state, it's just going to get worse. Because we tried them all.
What if after you remove the protonation state and it got a different pose in that pocket, and then like
we've tried,
it's also possible.
We've tried all the possible protonation states with all possible poses, and this is the best one. So anything else is worse.
Oh, right. Thanks. Gotcha.
So Yuhang, let's look at them and try and delineate what the structures are and see which ones are realistic and which ones are not. Okay.
Yeah.
All right, great. Really interesting. Thank you, everybody. Really fascinating. We'll post things online and we'll keep in touch. See you next month.
Nice meeting you, Jan.
See you.
See you. Bye.
Thanks, everyone.
Good meeting everybody.
Thanks, everyone.
Bye-bye.